Hello everyone. Today we are going to talk about spectral clustering. So you have learned about different kinds of clusterings like k-means, hierarchical, and so far. And also the density-based ones like dbScan. And today, this is the last type of clustering that we are going to learn. So what is the intuition behind spectral clustering? The intuition is like this, that whenever we see our original data in any form or shape, it can be of any type like numeric, categorical, or any kind of complex object, as long as we can find the similarity between our data points, and then we can represent that similarity as a kind of a graph, or in a similarity matrix between the data points, then we can have a lower representation of our data points according to that similarity matrix. Basically represent our data points in a lower dimensional space, like something similar to what we did in SVD, for example. But this one is based on the similarity matrix. And then when we have this lower dimensional representation of our data, then we can easily find clusters in this lower dimensional representation using simpler clustering algorithms such as k-means. Okay, so that is the intuition behind spectral clustering. So what we do is that usually in spectral clustering, we start with constructing a similarity matrix, okay, between our data points. So suppose that we have our data, we have a d-dimensional data, we have n data points and d features, and from that we can get a similarity matrix that is basically n by n similarity matrix, right? This similarity matrix is basically going to be built between each pair of data points that we have, right? And this is called similarity matrix. Sometimes it's called also affinity matrix. Okay, so what are the properties of this affinity or similarity matrix that we have? The properties is that first of all, let's call this matrix A, the similarity matrix A. So first of all, each element of the similarity matrix, let's call it Aij, is going to be larger than or equal to 0 for every I and j. So what does it mean? It means that if I pick a data point I and another data point j, the similarity between the two, or the affinity between the two, is going to be larger than or equal to 0. Okay, that's the first thing. The second thing is that Aij should be equal to Aji, or in other words, our affinity matrix is symmetric. So the similarity between data point I and data point j is equal to the similarity between data point j and data point A, right? Data point I, right? So these are the first two. And the third one is that A is positive semi-definite, which means that if we look at the eigenvalues of A, we can actually sort them according to them being the largest to the smallest. And all of the eigenvalues that we are going to have from A are going to be non-negative real numbers. So they are all going to be larger than or equal to 0. Okay, so this affinity matrix is basically showing it can be represented as a complete graph between our data points. So if I have my n data points, like data 1, 2, 3, 4, etc. N, the affinity matrix is as if I'm having a full graph between my data points, right? Full graph meaning that everyone are connected to each other if I have the full affinity matrix, and each link between two data points that I have is going to have a weight that is equal to the similarity between these two data points, for example, right? This is in case we have this complete graph. But the problem is that having a complete graph between our data points, it's too expensive. Why? Because if I want to have this complete similarity matrix, if I want to calculate all of these AIJs and have a full similarity matrix, then I have to calculate an order of n squared similarities. So that could be a lot, especially as we have more and more data points. So what people usually do is that they instead of calculating the similarities and keeping the similarities between every two pair of data points, they try to reduce the costs and use some kinds of approximation for that. So this is too expensive. So what we do is that we create some kind of approximation of affinity similarity matrix. So different things that we can do. For example, one of the ways that we can do that is to threshold the neighborhood epsilon neighborhood thresholding. This means that instead of calculating the similarity between each and every two data points, I only keep the similarity between a data point and the data points that fall in its epsilon neighborhood, right? So this is epsilon neighborhood thresholding. Actually, you can see that here in this graph that, for example, in this graph, our epsilon is 0.3. So the edges between our data points, or the similarities that we are going to keep, are these green edges. So we are going to only keep these green values in our affinity matrix, and the rest are going to be 0. For example, the similarity between these two is going to be equal to 0. So our matrix, our affinity matrix, is going to be more sparse, and so it's not as expensive to compute and keep it. That's epsilon neighborhood thresholding. Another way that people can reduce the cost is that we can have a k nearest neighbor graph. So basically, we are going to keep the similarity or affinity between each data point and its k nearest neighbor. So only, for example, if k is 2, I'm just going to keep the similarity of 3 with these two data points, 2 and 4, right? And the similarity of 4 with its own two nearest neighbors, for example, 5 and 3, right? And it is shown here in this graph. So for example, this k nearest neighbor graph, when k is equal to 5, the affinity values that we are going to keep, or similarity values that we are going to keep in the affinity matrix, are going to be these green edges. So here you see that we are still keeping some of the similarities, but we are also setting the rest of the similarities, like the similarity between these 2 points, to that there's no edge between them, to be equal to 0, right? So you can see that with different choices, we are going to have different affinity matrix graph. So building different types of affinity matrices is going to also affect the results that we are going to get. There is one issue with this KNN graph, and that is that if we just do the KNN graph, the problem would be that then we are going to lose this symmetric rule between for the similarity matrix. Basically, it means that the reason that this happens is that so the KNN graph itself is asymmetric, right? The reason is that the closest neighbor of a data point may not be in the closest neighbors of that other data point. Let me give you an example. Consider the k nearest neighbor graph as a graph of best friends. Okay. Like, for example, if k is 3, it's the graph of 3 best friends, right? But the problem that raises, that results in asymmetricness, is that, for example, your best friend may not consider you as one of their 3 best friends, right? So that will result in this KNN graph in its original form to be asymmetric. So what we do usually is that we try to do different things to resolve that. For example, we can take the union or intersection of best friend sets, right? So intersection means that we are going to only look at the mutual K and N, right? So you're going to keep someone as the best friends of the other person if the other person also thinks as the first person as their best friend. So anyways, so basically what we can do is that we can build in different ways this this similarity matrix or affinity matrix between our data points, right? And so any kind of similarity matrix, it can be represented as a graph also, right? Each data point is going to be one node in the graph, and the similarity value between two data points is going to be the weight of the edge that are between the two data points. Also, another general way is that sometimes our data actually comes in a graph or as a similarity matrix from the beginning. Suppose that, for example, you have a social network graph, which is the network between people who are connected with each other or are friends with each other. So our data is already in form of a graph, and if we want to find clusters of people or communities in that graph, then we can basically start with this graph to do this. So this clustering of graphs can be considered as a partitioning problem, graph partitioning problem also. So for example, suppose that you have an undirected graph with 6 nodes. So these 6 nodes are actually our 6 data points in the data, and the edges between them are the values that are in the affinity matrix. Now, if we consider a bipartitioning task, it is defined as dividing the nodes or vertices in the graph into 2 groups that are disjoint from each other, meaning that there is no link, no edges between these 2 groups. For example, in this image that we have here, if I want to kind of partition this graph into 2 groups, I would probably select these 2 and I would say, okay, this is one group and this is another group, and I'm dividing this whole graph into two parts. So I'm doing bipartitioning as a result. So although intuitively I selected these two groups or communities or clusters or partitions, but there is a question that, okay, how do you define a good partition? Why do you say that this is a good partition? And also, suppose that we have a measure that we say that, yes, this is a good partition, or no, this is not a good partition. But how can we actually identify such a good partition? So the way that we do it is that, thinking of what makes a good partition, we can think of this, that we want to find a partition that the number of within group connections are maximum and the number of between group connections are minimal. Meaning that when I am partitioning this graph and I'm selecting these two, the reason that I'm selecting these two is that I can observe that the three data points that are falling in group B, for example, are very well connected. They are all connected to each other. There are three links there. Similarly, the data points that are falling in group A are also very well connected. They are all connected to each other, right? So we have, after we do this partitioning, we have the maximum number of within group connections. Also, I can see that whenever I cut the graph like this, using excuse me, using this partitioning, like the blue line, I'm only cutting off two edges, right? So the number of between group connections that I'm going to remove or cut to get to the partitions is going to be minimum. It's going to be less, right? So that's how we can define a good partition. Now consider if I, for example, had separated 5 from the rest of the data points, then I was removing 1, 2, 3 edges, which is more than the 2 edges that I had cut at that point. So basically what we want to have is that internally, inside the groups, we want high affinity, right? And externally, or between the groups, we want low affinity. And that would be the definition of a good partitioning. So the way that we can define that, express that as an objective function, because we are always in data mining machine learning, what we are looking for is an objective function that we can express what we want to do mathematically so that we can optimize for that, right? So our objective function is going to be defined like this. We define something like a cut that is basically the set of edges that we are going to remove, right? So basically the external or low affinity ones that we want to minimize, the set of edges that we want to minimize are the ones that are between two partitions. What do we mean by between two partitions? How can we define them? It's the set of edges that they have one vertex in one partition, or one node in one partition, and their other node in another partition, right? For example, if you look at this edge here, you have one node in partition A and the other node at the end of it in partition B, right? So this is one of the edges that is going to be cut when we do partition this graph into A and B. Similarly, this is another one. So we want to basically minimize this, the cardinality of the edges that we are going to cut. So here we are removing 2 edges, so the cut is equal to 2. So how are we defining that? What we are saying is that we are looking at the weight of all the edges that one side of it, one node of this edge is in partition AI, while the other side of this edge or another node of it is in a partition except AI. So any partition except AI. Okay, so AI bar is any partition except AI. So if I go over all of my partitions and I count the number of edges or the weight of edges, if they are weighted, that they are, one side of them is in that partition and the other side of them is in another partition, then I can get some value of the cut, but you make sure that we are dividing this by 2. The reason is that if I'm doing this, for example, for this graph, once I is this partition, so I will count this edge once because one side of it is in A, so it's, if AI is A, I count this guy here, 1 plus, and this guy here also because one side is in A, the other side is not in A. Next time, I'm going to set AI to be partition B, and then again, I'm going to count this guy as one side of it is in B, the other side is not in B, and then I'm going to count this one again also because one side of it is in B, the other side is not in B. So basically, I'm counting each edge 2 times. That's why we have to divide this by 2 like this, so that we get the actual value of the cut or the number of edges or the weight of edges that we are cutting, which is going to be 2 here. All right. So that is going to define our cut weight for us. Now, what we want to do is usually we want to have the minimum cut possible, right? So what we're trying to do is to minimize the weight of the connections that we see between the partitions. So this can be our objective function that we want to find partitions A and B in a way that the cuts between A and B is going to be minimized, right? So A and B are going to be the arguments that are going to minimize this cut, and cut is defined like that. But sometimes this will result in a degenerate case. What do we mean by that? So look at this picture. Here, you can see that if you look at the whole graph, you can see that, okay, maybe just visually, it's a good idea to put all of these red nodes or data points into the same group or partition, and all of these green ones into the same group of or partition. Why? Because the red ones are all well connected to each other, and the green ones are kind of also well connected to each other. So if I do this kind of partitioning, then I'm going to get a minimum cut of 2, right? But if we really defining our criterion as minimum cut only, there is this other cut that is actually less than 2. So if I just select this one green node and partition according to cutting this edge, it's just one edge that I'm cutting. So the minimum cut here is going to be less than the blue cut. But then I'm getting this partition that is super imbalanced, right? One partition that I'm having is only going to have one node in it, and then all of the rest of the nodes are going to be clumped together in another partition. So maybe this is not a good idea to just rely on minimum cut, right? So maybe it's not a good idea to also just consider the external cluster connections, because the minimum cut is only considering the external cluster connections. What we have forgotten about is the internal cluster connectivity, or as we have talked about here, uh, we forgot about the high affinity that we want to happen inside each of the partitions, right? So we want not only the between clusters to have low affinity, but we want that inside the clusters we have high affinity. So that's why we can have different graph cut criteria depending on all of these things that we can consider. So for example, we can have normalized cuts, okay? In normalized cuts, we can consider how many data points, for example, are going to fall inside each of the partitions, in addition to considering what is the weight of the cut. Okay, so basically by dividing the weight of the cuts by the number of data points that will fall into a partition, what we are saying is that if the number of edges that we are cutting is more for partitions that have more data points inside them, then we are going to be more okay, compared to if we only cut one edge and there is going to be only one data point in that partition. Right, so that is one of the graph cut criteria that we can have. Okay, so this is called R cut. So it's going to, because we are penalizing the cut with the inverse ratio of number of data points inside each of the clusters, it is going to produce a more balanced clusters for us, meaning that the number of data points inside each of the clusters or partitions that we are going to have eventually are going to be more close to each other. Other kinds of cuts that we can have is, for example, so this can be also be called maximizing the so this is the minimizing the cut. Okay, so another things that we can have is that, for example, we can have average weight clustering, in which we are trying to maximize internal cluster or partition affinity. How are we going to do that? Because we are going to say our optimization now, J, of average weight is going to be, we want to maximize. What are we going to maximize? The internal partition affinity means that we are looking at the affinity or weight or similarity between the data points that are falling inside the same partition, or maybe I can say AI and AI, right? Divided by the number of data points that are in the AI and sum over all partitions that are there, right? So instead of looking at the weight or between the edges that fall, one node is in one partition and the other node is in another partition, I'm looking at the edges that both of their nodes are falling inside the same partition, meaning that that is representing the internal or inside partition affinity. And I want the inside partition affinity to be maximum. Right. Another one is, well, we have seen the ratio cut. Another one that we can have, so this is basically called ratio cut. That's why R. right? Another one that we can have is normalized cut. And basically, it's a normalized version of ratio cut. So what we want to do is that we want to minimize. So this one was maximize, this is minimize. What we want to minimize is that over all partitions, I want to minimize the weight or affinity between partitions. So I have AI here and I have AI bar here, which is whatever that is not AI, divided by the weight between AI and all partitions, including AI. Okay, so basically this is all possible so all possible distances or affinities that the data points in AI have with every other data point, right? So this is one of the cuts that we can have. So it's kind of like including both average and ratio cuts in it, right? Because what I can do is that I can rewrite, I can say this summation I equals to 1 to k is basically, if I have WAI and AI bar, WAI and everyone, I can rewrite this part. Sorry. I can rewrite this part because it's between all the data points that are in AI and everyone else. So I can divide this into two parts. One is between AI and AI itself, and the other one is between AI and AI bar, right? So the data points that are inside AI and the data points that are outside AI. Okay. So it's as if we are having both the average cuts. So this part is going to come from the average weight. And this part that is coming from the ratio cut together in it, right? So basically, we can define different kinds of graph cut criteria, right? So not only we can build our graph in different ways, but also when we want to partition our graph into different partitions or clusters, depending on different kinds of criteria that we define, we are going to get different kinds of clusters as a result, right? Now, let's look at the matrix representation once more. So we said that a graph is equivalent of an adjacency matrix or affinity matrix, right? And it's an n by n matrix because we have n data points. And if there is an edge between node I and j, then we are going to have the a, I, and j to be equal to 1 or equal to weight or affinity between the two. Okay, otherwise it's going to be 0. And because we don't have self loops, we just set the diagonal elements to be 0 also. So again, it's a symmetric matrix with eigenvectors real and also eigenvalues being orthogonal. Now, if I want to represent the degree matrix, what is a degree? First of all, let's talk about the degree in a graph. The degree of a node in a graph is basically the number of edges. If it is indirected graph, is the number of edges that are connected to that node. So the degree of node 5, for example, here is 3 because there are 3 edges that are connected to node 5. The degree of node 2 is 2 because there are 2 edges that are connected to node 2. Now, if I want to calculate the degree of each of these data points, then I have a degree for each of them, right? So I have 6 data points, so I have 6 different degrees, one for each of the data points. I can represent that also in an n by n diagonal matrix. Basically, the degree of each node is going to be represented in the diagonal that that node has. For example, here, this is the degree of node 1, and we show it at the diagonal 1, 1. Here, we have the degree of node 4, we show it at the diagonal 4, 4, right? And here we have the degree of node 6, we show it at the diagonal node 6. So this is called the degree matrix for a graph. Okay, everywhere else we have zeros on the diagonal, we have the degree values. Basically, if we want to talk about the relationship between affinity matrix and the degree matrix, what we can say is that if I sum up the values in every row, for example, then I'm going to get the degree of that node in that row. For example, for node 1, the rows, if I sum up the rows here, I have 1 and then 2 and 3, right? And the degree of node 1 is actually 3 also. Why? Because these ones here are showing if node 5 is connected to node 1, if node 3 is connected to node 1, if node 2 is connected to node 1, right? So I have 3 different nodes that are connected to node 1, meaning that I have 1, 2, 3 edges around node 1, meaning that the degree of node 1 is going to be 3, right? We can do the same with the column, doesn't matter if it's row or if it's column. So the summation of rows in affinity matrix is going to give us the diagonals of the degree matrix, or the summation of columns in affinity matrix is going to give us the diagonals in the affinity matrix. Okay. Now, another matrix that is important to know when we have graphs is the Laplacian matrix. Laplacian is basically calculated according to the degree matrix and the affinity matrix, and it is calculated like this. So it's equal to D minus A, meaning that, so on the diagonals, we are going to have the same values as the D matrix, so the degree of each of the nodes. But on the non-diagonals, what we are going to have is the negative of similarity values or adjacency values, okay? Again, this Laplacian matrix is going to be positive semi-definite, so it's going to have non-negative real eigenvalues, and its eigenvectors are going to be real and orthogonal. Okay. So we have talked about Laplacian degree and affinity, but let's see why they are important when we are talking about spectral clustering or graph clustering. Okay, so let's assume that we have this interesting representation of our clusters. Suppose that when we have a cluster, for each cluster, we have a vector that is basically, let's call it X, okay, that is having length n, one for each data point. So this n is number of data points that we have. And the way that we represent each cluster is that if a data point belongs to cluster, then xi in that cluster is going to be 1, otherwise it's going to be 0, right? So, for example, if I have 6 data points, 1, 2, 3, 4, 5, 6, right? And I want to represent partition A in our example with this vector. So basically, this is our X for partition A. I'm going to have 1, 1, 1, because data points 1 and 2 and 3, they all belong to partition A in our example. And then 0, 0, 0, because 4, 5, 6, they do not belong to partition A. On the other hand, if I want to represent my partition B, I'm going to have 0, 0, 0, 1, 1, 1, right? Because 4, 5, 6 were in partition B, and 1, 2, 3 were not in partition B. Okay. So now that I have defined my clusters in form of these vectors, I can define some new things about my clusters, right? So what can I say about this? So first of all, because our partitions are mutually exclusive, meaning that one data point either belongs to partition B or partition A, right? So one data point cannot be in the same cluster. It can happen in some other fuzzy kind of clusterings, but here in this course and what we are discussing right now, we don't have that happening. So one data point only falls into one partition. Then if I have two clusters, x1 and x2, then the dot product of the vectors of these two clusters is going to be equal to 0, right? So for example, in our example, if we take the dot product of x of A transpose x of B, it's going to be equal to 0, because wherever A is non-zero, B is going to be 0, and vice versa. Whenever A is 0, B is going to be non-zero, right? So we are going to always have x1 transpose x2 between every 1 and 2 to be equal to 0. Another thing that we are going to have is that the number of data points that fall into each cluster is going to be equal to x1 transpose x1, the representation of cluster dot product with itself, right? So for example, I have 3 data points in XA. Now if I take XA transpose XA, I'm going to have 1 multiplied by 1 plus 1 multiplied by 1 plus 1 multiplied by 1 plus 0, 0, 0. That is going to be equal to 3, right? So if I also put all of my clusters together, so if I have a large matrix X that is happening to be my x1 and x2, etc. So all of my partitions together. So here, for example, if I put XA and XB next to each other, then the number of data points in total that I'm going to have is going to be equal to this huge X transpose X. Okay, so after I have these, then I also can represent the cut between two clusters like this. I can have, if I have a kind of if I want to calculate the cut between A1 and A2, what I can say is that it's basically equivalent to X1 transpose A X2, right? Why? Because A has its all the affinity relations in it. It has all the similarity relations in it, right? So basically, when I put A here in between X1 transpose and X2, I am calculating the weight of the cut between the two. So I'm calculating the number of data points, the number of edges that one side of them is falling in A1 and the other side is falling in A2. Another thing that I can have is that the affinity between data points in A1 and all other data points that I have, my whole data, is going to be equal to my X1, which is related to A1, transpose D, okay, and X. D is my degree matrix. So this is affinity or adjacency. This is my degree. So basically, this is going to count the degree of the sum degree of everyone in my partition. And also another thing that we are going to have is that the weight between each partition and everyone else then, now I have the weight between each partition and everyone in the data. I have the weight between each partition inside each partition, because this means that the weight inside the partition is going to be basically A1 and A1, which is going to be X1 transpose A X1, right? So I have the weight between A1 and A1. I have the weight between A1 and everyone, including the ones that are inside A1. So if I want to calculate the weight between AI, the ones that are in AI and the ones that are not in AI, it's going to be equal to W of A1 and V minus W of A1 and A1, right? We have seen that, and which is basically equal to x1t dx x1 minus x1t a x1, which is equivalent to x1t d minus a x1. Okay, so why did we do all of this? It's because you remember these different cuts that we had? Well, now what we can do is represent each of these different cuts in the form of affinity or adjacency matrices and degree matrices, and this guy is the Laplacian matrix, right? So basically it means that we can represent all of these cuts and the partitioning objective function in terms of the different matrices. Depending on which objective function we are interested in, we are going to have a different representation of the objective. So if it's, for example, if it's this cut, the ratio cut, then we are going to be more interested in the Laplacian one, right? So let's see an example right now. So we have seen all of this. Now let's see an example of that. So for example, suppose that I'm interested in the average weight clustering. Okay, so in this one. the average weight clustering. So the average weight clustering, what we want to do is we want to maximize this average weight thing, which is the summation over all of my partitions. And then what we had above was W of AI and AI, right? Which we saw that it's basically, it's a XI transpose affinity XI, right? And then divided by the size of AI. That size of AI, we have seen that it's basically equal to XI transpose XI, right? So this is basically norm of XI squared, okay? So now our goal is to find a partition that maximizes this objective function, right? Now, let's see if we can rewrite this objective function in some other way. So, for example, now that I have these xi transpose and xi's on both sides, I can say that this is equal to 1 to k. I separate these xi transpose. So I would say this is xi over norm of xi here, transpose a, and then I separate this part. On the right hand side, it's xi over norm of xi, right? So I had norm of xi squared. I basically put one of them here, one of them there, and I have this form. Now, if we look at this, we'll see that this xi over norm of xi is basically a vector of norm 1, because we are dividing by square of by norm of x1. So it's going to be of norm 1 in the direction of xi, right? So what we can do is that we can say, let's call this guy, this vector of norm 1 in the direction of xi, to be equal to yi. So in other words, yi is xi over norm of xi. Okay, then, so our objective function, we can rewrite it like this. We want to maximize, what do we want to maximize? We want to maximize the sum over 1 to k yi transpose a yi. And we know that yi, norm of yi is 1, because it's a vector of norm 1. And also, we know that yi transpose yj is equal to 0, right? Because xi transpose xj is equal to 0. We have seen it here, right? Because the partitions are exclusive, mutually exclusive. Okay, so what does this mean? These two together means that yi's are orthonormal. They are orthogonal, and also they are normalized with norm 1. Okay, so basically this problem here with this condition that we have yi is to be orthonormal is going to be equivalent to finding, this is equivalent to finding the k largest eigenvectors of A. Okay, so basically, if we set A y1 equals to lambda y1, y1 being the largest eigenvector and lambda 1 being the largest eigenvalue, this is going to give us the maximum of this J. Okay, so that is good. So so far so good. So by solving this, we can get to the maximum of this value. But then there is a problem here. And the problem is that the eigenvectors that we get by solving this equation, they are not going to be discrete. So what do we mean? What we are looking for is this kind of vectors for partitions, that if a data point belongs to a partition, we have 1, otherwise we have 0. So the values are zeros or ones. But the yi's that we are going to get here, they are not going to be zeros or ones, right? So what can we do to solve this? There are different ways that we can solve this. We can set the yi and say that yi belongs to either 0 or 1. Okay, but the problem is that this is too complex. Solving this problem needs a lot of effort. It's going to be NP hard. So instead of that, what we can do is that we can say, okay, we are going to keep yi and we're going to be okay with it. And we keep that as an approximation to our problem. So basically, for example, what we can do is that we can select the yi's with most of the values to be ones and the yi's with the least of the values to be zeros. Okay, so that's one way that we can deal with it. And we are going to see more ways later also. Okay, so that's, for example, for the weighted average cut. Another thing that we can have is, for example, if we want to we want to work on the ratio cut. Okay, so the ratio cut. So this one was sorry, average weight. Okay, now suppose that we want to look at the ratio cut minimization, right? So what we want to do here, we want to minimize ratio cut, which was, what was our ratio cut? It was what we have there. So summation of cut between AI and AI bar, sigma I1 to K, summation of WAI and the ones that are not AI, right? And we wanted to divide that by the number of data points in AI. Okay. So now we can use all of these some of these 5 equations there. For example, we know we can use 5 for the numerator. So here we have xi d minus a xi, and forgot the sigma. And then for the denominator, of course, again, we have xi transpose xi. Right? So again, if we define yi to be xi divided by norm of xi, then we are going to have this minimum of ratio cut to be equivalent of summation I equals to 1 to k yi transpose d minus a yi. Okay, so now because we are trying to minimize this, what we are going to have is, again, we have yi's are orthonormal. And so if we take the eigenvalue, eigenvector decomposition of this matrix, Laplacian matrix, then and we look at the smallest eigenvalues. So yi is going to be corresponding to the smallest eigenvalues of this matrix L, which is D minus A, Laplacian matrix, right? So here we are having the largest one because we try to maximize that J of AW, but because here we are minimizing, we're going to find the smallest ones. Okay, so now suppose that I'm trying to do, we can try this for all kinds of cuts. So if I want to do normalized cut, what I'm going to have is that I'm trying to minimize of normalized cut, which is basically going to translate into 1 to k xi transpose, again d minus a xi divided by, this time xi transpose d xi, right? So this time what we are going to say is that we can say we can rewrite this d as d to the 1/2 multiplied by d to the 1/2, right? So basically what I can define yi this time, I'm going to say yi is equal to xi d to the 1/2 divided by xi d to the 1/2. Okay, so basically what we are going to do, let me actually open this up and show it to you. What we are going to do is going to be equal to sigma I equals to 1 to k. Now we will say xi transpose d minus 1/2 plus d minus 1/2. So we just add a d to the 1/2. So a square root of d square 1 over square root of d above here. It doesn't change anything, right? If I add that, and then d minus a. Now, again, I'm going to add d to the minus 1/2, d to the 1/2, xi here, okay? And then the denominator, I'm going to say it's equal to xi transpose d to the 1/2, d to the 1/2, and xi. Now, what I can do, I can say that, oh, I can check this one out, and then I can check this one also out. So basically, we can say that if we set yi is equal to d to 1/2 xi over norm of d 1/2 xi, then we can rewrite this normalized cut objective function like this. We can say that it's equal to I equals to 1 to k. Now we're going to have yi and then d 1/2 d minus a, which is L, basically d minus 1/2 yi, right? So the reason that we can do that is that so the 1/2 exists because D is diagonal, symmetric diagonal, right? And also because it's diagonal, then D transpose and D are the same as each other, right? So this would be our L. So now this whole thing, we want to minimize the normalized cut. So this whole thing translates into finding the smallest eigenvectors of this matrix. So basically, the equation that we have is similar to finding smallest eigenvectors of d minus d1 half L d1 minus. Okay, so we can find one smallest eigenvector of this or k smallest eigenvectors of it. So we are going to see yk in very soon. But one other thing that we have to make sure that we are looking at is that what do we mean when we are talking about the smallest eigenvectors? What are the smallest eigenvectors or eigenvalues of the matrices that we have? So matrix L, the Laplacian matrix, we have to note that the rank of this matrix is n minus 1. You remember that L was n by n, and L was d minus a, right? But the rank of L is n minus 1. What do we mean by the rank of L being n minus 1? We mean that if we have an n by n matrix, Laplacian matrix, we can, for example, rewrite one of its columns, suppose the last columns, as a linear combination of the rest of these columns. So if I say I have Li as a column, L I as the column I of L, then I can rewrite, for example, Ln as a weighted combination of all other columns. I is equal to 1 to n minus 1. Okay, the reason is that we know that L is equal to D minus A, and A is symmetric, D is diagonal, and they have this, D is the degree of each of the nodes, A is the edges that go through every other node. So we can basically calculate this last column, even if we don't know the values in it. Because, for example, this here is minus affinity between node 1 and node n, and we already have it there. So this is going to also be the minus affinity between node n and node 1, right? And they are equal to each other. And with different ways, we can actually get to this last column as a linear combination of all other columns. So that's why the rank of L is going to be n minus 1. Now, what does it mean that the rank of L is n minus 1 at most? It means that one of the eigenvalues after we do eigendecomposition, it's going to be 0. So when we arrange our eigenvalues, we said that it's a positive semi-definite matrix, so we can rearrange our eigenvalues like this. All the eigenvalues are going to be non-negative and real numbers, right? So far what we had, we said that for any positive semi-definite matrix, we have this situation that all the eigenvalues are real and non-negative. But because the rank is n minus 1, we are sure that the last eigenvalue is actually equal to 0. Okay, what does it mean in terms of what we are looking at? It means that when the last eigenvalue is equal to 0, the last eigenvector is also always like 1 or always the same number. It doesn't matter what number it is. Okay, so it means that when we are choosing the smallest, when we are looking at the smallest eigenvectors here and there, the first smallest, like this one, it doesn't give us any information. So what we are looking at, we have to start looking at the second smallest eigenvalue and the eigenvector that correspond to it. Okay, so basically here, what we are going to do is that we are going to look at the second smallest eigenvalues of Laplacian. And also, if we want to look at more than one of those, we can look at the second one until the kth one, for example. So this way we have k minus 1 eigenvectors that we are looking at. All right, so that's another thing that we can do. Now, let's go back and look at this in another setting. So another way that we can look at it is that what we are looking for is a sum f, and that it acts kind of like our yi, right? It's basically going to give us the membership of each data point into each of the partitions. But because we know that L, or Laplacian, it has a quadratic form and symmetric positive semi-definite, then we know that there exists this F, that this is correct. It happens for it. And what we are trying to find, for example, when we want to minimize the ratio cut, is that it's the minimization of ratio cut is going to be equivalent to find the F that F prime LF, so F transpose LF, is going to be minimized. So remember, this F is similar to the YI that we have discussed so far. And then it's a hard problem to find this. So we can relax it a little bit and say that if the node belongs to the partition, we instead of having zeros and ones, we are going to have some real number, like square root of number of points in outside A divided by number of points inside A, and negative of the inverse of the ratio if the node is not belonging to A. But still, that is going to be too difficult. That's why another approximation for that is going to be with the second eigenvector, right? So it's basically another way to look at what we have already looked at. So this is going to give us the second eigenvector, which in turn can be translated in how much each data point belongs to each of the partitions. So, so far we have learned how to define a good partition of the graph. We define a cut, and we try to, for example, minimize the graph cut or maximize the within partition weights. And we have learned how to efficiently identify this kind of a partition, right? So we are going to use approximation using eigenvalue, eigenvector decomposition. Now let's look at spectral clustering as a whole. Spectral clustering has three basic stages. The first stage is pre-processing. In pre-processing, we are given a data set, and we are going to construct a graph representation of that data set, or a matrix representation of the graph. So if our data is an n by d, n is the number of data points and d is features that we have, we are going to construct an n by n affinity matrix from it, or Laplacian matrix, or any kind of graph representation from our data. Note that with different kinds of similarity measures, we get different kinds of graphs or matrices. We have seen that before. The second step is decomposition. So we are going to compute the eigenvalue, eigenvectors of that graph or matrix that represents that graph. And with that, we are getting those yi's that we have talked about, right? It's, for example, if it's Laplacian, we are going to start from the second smallest eigenvector. And for example, we can get to the kth smallest. So from a d-dimensional space, original mapping between n and d features, we got to the n by n graph space, and now using these eigenvectors, what we are going to have is going to be n by k-1 dimensional matrix again, because each of the eigenvectors are an n dimensional vector, right? So this is going to be the second smallest, etc. This is going to be the kth smallest. So this is the eigenvector associated with the kth smallest eigenvalue. This, for example, right? So we are having a mapping between our data points and a lower dimensional representation of our data. And the third step is the grouping. So in grouping, what we do is that according to this mapping that we just got, we're going to assign data points to 2 or more clusters based on this new representation that we are having, this new representation. Okay, let's see what happens here. So looking at our bi-partitioning example, you remember that in the pre-processing, we could build this Laplacian matrix. We built that, right? And then we could do the decomposition. If we do the decomposition, this vector is going to be the vector of our eigenvalues. And this matrix is the matrix of our eigenvectors. We can see that the first eigenvalue is 0, because it's Laplacian, and we have talked about it already. And the eigenvector for that first eigenvalue, all the values there are the same, right? So we are going to ignore this first one, and we are going to look at the second one, the second eigenvalue, and the eigenvector that corresponds to that eigenvalue. Now, assume that we are just looking at one yi at this point. We don't go to the third or fourth or etc., etc. So we are only looking at this one eigenvector here. And if we look at the values in this eigenvector, we can see that each node or each data point has a value there, right? So the eigenvector value for node 1, 2, and 3 are all positive. And for nodes 4, 5, and 6, they are all negative. So we kind of need to use this vector, yi, or y, basically the second eigenvector, to find the clusters between the data points. And looking at the values, we can get an idea, an intuition that how can we do that? So what we can do is that we can say, okay, I need to split these data points, and we can look at this one value as one feature that I have, right? Now, if I look at these features, because for half of the data points they are positive, for the other half they are negative, I can say, okay, I can split my cluster according to the values being positive or negative. So we are splitting at 0, right? If it's more than 0, it's one partition. If it's less than 0, it's the other partition. So that is a naive approach to do this, an easy approach to do this. Other approaches also exist. For example, another thing that we can do is that now that we are in a one-dimensional space, we can try to minimize the normalized cut in this one-dimensional space. And what I mean is that we can swipe over the ordering of nodes and have the cut here, or here, etc., and calculate what would give us the minimum cut possible. But it's really too expensive to do. So what we usually do is that in the naive approach is that we order the data points according to their eigenvector values from maximum to minimum. For example, for this vector, what we do is that we order according to the values. For example, we can see that 0.6 is the maximum for data point 2, then 0.3 for data point 1, 0.3 for data point 3, and then minus 0.3 for 4, minus 0.3 for 5, and minus 0.6 for 6. Okay, so then what we can do is to actually plot these values, right? I can say that after I have ordered all of my data points, I can plot the values of the eigenvectors for these data points. So here I have data point 2 and it's 0.6, and then I have data point 1 and it's 0.3. I have data point 3, it's also 0.3. Then I have data point 4, it's now minus 0.3. And I have data point 5, also minus 0.3, so 4, 5, and data point 6, I have minus 0.6. So if I actually sketch that and connect everything together, what I'm seeing is that I can see a huge gap between data point 3 and data point 4, and then I can say, oh, all right, so if I split at this point, I'm going to get a good cluster because the difference between the eigenvectors of these two data points are too large. Let's see an example of that. So if we do that for this graph, we can actually see that there are two clusters in this graph, or two big partitions in this graph. So now if I sketch, if I do the eigenvector decomposition of this graph and look at the second eigenvector, second smallest eigenvector of the Laplacian for this graph, and then order the value of this second eigenvector for different data points. Now, this is from smallest to largest in this kind of a plot. What I can see is that for some of the data points, these values are all close to each other. So for example, for this cluster, this partition, everyone are close to each other. For these other values, they are also close to each other. For example, for this partition, and then I see a huge gap here between the two eigenvector values. So I would say, okay, I'm going to cut at this point, which represents this cut here. Okay. Now, what happens if my data actually has more than two clusters? So here, what we see in this example is that we can see that there are two big partitions, right? Because they are only connected with one link. So there are two big partitions that we have, but inside these two big partitions, there are two smaller partitions each, that they are connected by two links or two edges, right? So if we actually do the same and plot the second eigenvector of the Laplacian of this graph, we are going to see something like this. If we order them from minimum to maximum, we're going to see something like this. So we do see this huge gap here, which basically belongs to splitting the data into two large partitions, but also we see two smaller gaps here, right? Which is for each of these sub-partitions that we have. All right, so so far we have only looked at rank in the second eigenvector. So only one eigenvector of this whole data. But we can look at more than one eigenvector, right? Why do we need to do that? So one of the reasons we want to do that is to have a k partitions instead of two partitions. So look at this example. For example, if we want to have 4 partitions instead of this 2 partitions and that have this kind of a split. So we can have 2 ways to do it. One is that we can do recursive bipartitioning, meaning that we partition our data once into 2 partitions. Then we go inside each of these 2 partitions and we repartition them again, create the Laplacian matrix, do the decomposition, and create 2 partitions. So doing this recursively, there is a problem with it. It's kind of like a hierarchical clustering, but the problem is that it's inefficient because we have to redo this building the Laplacian and doing the eigenvalue eigenvector decomposition again and again, and it's also unstable. Another way to look at it is that instead of looking at only the second smallest eigenvector, that is just one vector, we can look at multiple of them, right? So you remember that we were talking about looking at the second to the kth smallest eigenvectors. Basically, the eigenvectors that are associated with the second to kth smallest eigenvalues, right? So we can look at multiple eigenvectors at the same time, and then instead of having one vector to split the data, we have k-1 vectors to split the data. But the problem is that, okay, when I had one vector, I could just sort the values in that one vector and decide based on the gap that we had there. But how can I do it with k different vectors? Or k-1 different vectors? The way that we can do that is that we can now run a easy, like a simple clustering algorithm on this matrix that we have that is basically an n by k-1 dimensional matrix, right? This is a common, more common used approach, and it is also preferable. It gives better results to us. All right. So basically, the reason that we can use multiple eigenvectors is that it is, first of all, is a good approximator for the optimal cut. So the optimal clustering that we can have with different k or k-1 clusters. And it's going to give us more cohesive clusters. So that increases the unevenness in data distribution that we are going to see, but within each of the partitions, we are going to see more affinity or similarity. And basically, that's good. Also, between the partitions, we are going to see less affinity. And it's going to basically give us a well-separated data. So as a summarization of what we have seen so far in our clustering, in our spectral clustering, the complexity is going to be an order of n to the 3 or less, depending on how we are using it, what kind of a similarity or affinity matrix we use, and what kind of algorithm we use for eigenvalue, eigenvector decomposition. The number of clusters in spectral clustering, we need to pre-specify them. Why? Because of 2 reasons. One is that if we want to do the k-way clustering, so I need to choose what number of eigenvectors I want to look at, right? Number of eigenvectors. I want to look at. And also, after we have selected the k smallest eigenvectors, for example, then I need to run k-means on it, right? And so I need to specify that k for the k-means also. Usually, the practice is that if you have k eigenvectors, you are going to use the same k for doing the k-means. So if I choose 3 eigenvectors as my lower dimensional representation of the data, I'm going to find 3 clusters in k-means for that. But that's just practice. The stability of spectral clustering, it is stable because up to finding the eigenvectors, it is going to be deterministic. Meaning that if you start with the same graph matrix, for example, the same Laplacian matrix, you're always going to get the same eigenvalues and the same eigenvectors after decomposing that matrix. You may see different results depending on the results of the k-means that you are running afterwards on this, but before that, everything is deterministic. It is not optimal, of course, because it's an NP-hard problem to find the optimal clustering. And it also works for non-convex clusters. And the reason is that we are looking at the similarity or affinity or graph between the data points. So if we define our similarity to be able to be able to handle non-convexity, then we are going to be okay with that kind of data. And also it's okay for non-Euclidean data. It's because we are working with similarities again, we are going to be fine in working with any kind and type of data as long as we can define some similarity between them, okay? But the problem with spectral clustering is that it's not really good in handling noise. And the reason is that when we are doing the partitionings, we are always looking at finding the minimum cut possible. And suppose that there are some noises in the data, the spectral clustering eventually tries to fit those outliers or noise data points somehow in some of the partitions, and that's going to skew the partitions for us. So it's not really good in handling the noise. So this is the end of all clustering algorithms that we are going to see in this class.